Our third speaker is going to be presenting from online, so Aashwin.
Yeah, would it be fine if I just shared my screen?
Yeah, we're seeing it, so
okay.
You can.
Awesome. I'll get started whenever you wish, sir.
Yeah, you can start.
All right. Well, this talk just focuses on the problem of data generation rates and how they're leaving the rate of scientific analyses in the dust, especially at light sources. In this setting, what practices, principles, and software tools are we developing at SLAC to address this issue? All right. So as we try to illustrate with this figure, there's a widening gap between the rate of data generation and that of scientific analyses at light sources. The rate of generation of raw data is increasing exponentially, while that of analyses is increasing linearly or polynomially if you've got a lot of grad students. So a good example of this would be the increasing brightness of light sources, such as the Advanced Photon Source or the high repetition rate upgrade of LCLS. This opens pathways for and opportunities to leverage understanding and insights and gain mastery of new technologies. However, these insights come with increasingly complex experiments requiring extreme precision over inordinately long durations. Just as an illustration, experiments at the upcoming LCLS-II-HE will require the X-ray beam to be within a fraction of a micron in diameter with a Poynting stability of a few nano-radians at the end of a kilometer-long electron accelerator, a 100-meter-long undulator section, and tens of meters of X-ray optics. Additionally, the increased complexity and throughput of these experiments from enhanced brightness will produce raw data at over 1 terabyte per second, rivaling the largest data generation sources in the world, requiring us to bridge this gap between data collection and that of scientific analysis. Now, there are different elements in this experimental pipeline at SLAC, as we have illustrated in this figure, starting from the injector to the accelerator onto X-ray optics, reaching an end station, and then on to post-processing. Till recently, all these stages were using different platforms, different software, different protocols, often developed completely independently, and this led to a problem akin to the Tower of Babel, where different elements may be rowing along different directions altogether. To address this, we've started to institute a start-to-end framework for modeling, control, and data processing. The first thing in this end-to-end framework would be a common platform across the different elements of the pipeline. This is essential for maintainability and debugging, as well as for compatibility and integration of different modules in this pipeline. For instance, using the same platform ensures that the same APIs are utilized in each module across all stages. This also renders the chain of modules easier to maintain and debug, for instance, when updates are released for libraries and so on and forth. Another cornerstone of this start-to-end approach is developing effective coordination between different teams of subject matter experts in modeling and controlling different physical phenomena inside the LCLS facility. Due to differences in the physical laws that govern the electron and X-ray beam dynamics, the modeling and control of these beams is usually handled separately by different teams. However, the teams of modeling and control, the problems in each one of these subfields often share significant similarities. As a result, the same machine learning algorithms or approaches can be used directly or adapted slightly to port them over the challenges in different facets. And this is one of the key things that we are trying to do. Moving on, we moved to something more less ambiguous, so to speak. With this preamble, we'd like to move over to specifics where we highlight the use of some of these tools developed at SLAC for common problems at light sources. Like, as we'd mentioned earlier, libraries developed at SLAC, we'd like to highlight the XOpt package. The key objective of this library, the XOpt package, is to enable flexible optimization with minimal coding for the end user. As long as the function to be optimized can be integrated into Python, it can be optimized with state-of-the-art algorithms, hopefully, in less than about 5 lines of code from the end user. The sandbox problem that we're looking at is something that was just hinted at in the last talk, which is the split and delay. As I've tried to outline in this figure, this consists of 2 branches, the channel cut branch outlined in blue and the delay branch with 12 degrees of freedom outlined in red. This delay range lies between about 5 to 500 picoseconds. With LCLS-II-HE, this split and delay will be crucial for ultra-fast studies of complex materials. So we are really trying to make sure that our control and alignment of this system is very efficient and does not create a bottleneck. Now, the alignment of this split and delay requires a spatial overlap between these 2 beams, the red line and the blue line, so to speak, with optimized intensity at the output. For instance, at XPCS, this can provide twin pulses with custom delays. Both these branches must be aligned to the same photon energy within about 0.1 eV with almost perfect overlap and matched intensities. Currently, these are aligned sequentially using beamline scientists from right to left by an experienced operator using intermediate sensors, because it takes, like, a human being can't handle more than about 2 or 3 degrees of freedom. And it takes about 4 hours to 5 hours for this alignment procedure. And the final setting may not be the global optimum, so to speak. And even once you've reached this optimum, because of temporal drift in the system, we need to interrupt the experiment after every about 10 to 15 minutes to realign the system, which is referred to as just drift correction. Now, the key issue that arises with such crystal optics is that they're akin to their optimization is akin to the search for a needle in a haystack. So in the last few months, we've come up with a domain-informed Bayesian optimization approach where the active subspaces, or the most influential directions in input space, are learned from data. And then the optimization focuses along these directions to get the maximal bang for its buck. And the optimization also modulates the trade-off between exploration and exploitation to find that darn needle. Here I'm showing just some mean values in the dark lines and about a 25 to 75 percentile zone in the gray shade over 50 different experiments using classical Bayesian optimization versus this learned domain-informed Bayesian optimization. So using this algorithm, what we can see between the left, which is classical, and the right, which is the domain-informed, we are able to find much better or higher intensities for the split and delay quite consistently. If we just move over to the beam position error, we're similarly able to find much better or lower beam position errors for the split and delay consistently. For an apples-to-apples comparison, the human operator would take about 4 hours for this alignment, and we can do this with about 10 minutes using this domain-informed Bayesian optimization procedure. As a final issue, we have the stabilization of the experiment due to temporal drift, where I'd said after about every 10 minutes, we need to realign. And if we use time-varying Bayesian optimization for this, we can control the beam over a lengthy period of hours. Here, the dark circles exhibit the TVBO optimization-based samples, and the dark lines show what the beam would have become markedly non-aligned in a short time if left to its own devices. The key idea to reiterate, we are developing all these algorithms for common problems and light sources, and we are integrating these into packages which can be ported over to other light sources too when used with minimal coding. Here I'm just telling you what I've told you with reiteration of some key points, and for more details, you can refer to the references given at the bottom of the slide. Thank you, sir.